Hello, everybody. I believe this is going to be our 29th video lecture, and that the 28th video lecture was one that was recorded while no one was here to make up for 2 days that I was absent. For those of you who got the email, you know, but for those of you maybe who didn't, my wife was hospitalized on Thursday evening, and she remained in the hospital till Monday afternoon. Everything's getting better for her, but she's still having some pain. But she's improving, so she was able to go to work on Tuesday and able to go to work today. And so I want to thank everybody who thought nice thoughts for us, and we're going to be okay. Everything's all right. In that video that was created and posted, maybe you haven't had a chance to look at it, but what we covered was the following. So first of all, we had the something called sequential criteria for function limits. And it said the following. It says the following are equivalent. I'll just read it shortly. And that is, the first statement is, the limit as x goes to c of f of x equals L. I'm not putting any prefacing remarks about this. The theorem does have prefacing remarks. What the domain of f is, c is the cluster point of the domain. Anyway, I'm saying that. And two, if x of n is any sequence in the domain A of L, with x of n being different than c, and yet the limit as n goes to infinity of x of n equals c, then that forces the limit as n goes to infinity of f of x of n, that's a sequence of output values, to be equal to L. So those two statements are equivalent, and what that does is it gives us a means by which to relate limits of functions to limits of sequences. So that's what we're having here. That's something we actually had written 2 lectures ago, and it started proving it, but I finished it in the lecture that no one was here for, but I just posted. In addition, we also in that lecture 28 I had stated a fact about limits of algebraic combinations of functions. So here's what it said. It said that if we let f and g both be functions that have domain A and are real value functions, where, or and, with, I'll say, C being a cluster point of A, and the limit as x going to C of f of x, that exists, let's call it L. And the limit as x goes to C of g of x exists, let's call it M. Then we have 4 statements. One is that the limit as x goes to C of the addition of functions f plus g acting on x, that will be equal to L plus M. 2, here I'll write 2 over here to the side. The limit as x goes to C of f minus g acting on x, that's equal to L minus M. So it's the subtraction of the limits of each individual parts of the function. 3, the limit as x goes to C of f times g acting on x is equal to L times M. And finally, if g of x is never equal to 0, so it's always different from 0, and that's for all x element of a, and if m is different from 0, then the limit as x goes to c, let me write this up here. The limit as x goes to c of f divided by g acting on x is the same thing as L over M. What I have just written is a theorem that's analogous to a theorem that we had about convergent sequences. Okay? Remember, if we had two convergent sequences and we add them, it converged, and what it converged to was the addition of the limits. Same thing for the subtraction, multiplication, and division. Audrey, is that okay?
Like I said, I didn't get to the last 10 minutes. So, like, is this different than the definition that you did in the video? Where
Yes.
okay,
So I had
that's all
definitions
right.
of what
Okay.
F and G were.
All right, I'm sorry.
It's nothing to be sorry about. I had definitions of what F plus G were, and F minus G, and F times G, and F divided by G.
Thank
But
you.
here, this is a theorem that we ended with, and I had done the first two parts, the proofs of it.
Okay.
And the way that these proofs went, and the way that all the proofs are going to go, so the first two proofs I did in lecture 28, and the way that the last two are going to go is similar to the first two, and they're going to be dependent on the sequential criteria for function limits. So I'd like to do this in front of you. Let us move to the proofs of the third and fourth. So I'm going to move all the way over here this time. Yeah, we're going to use this. Okay, so here's what I'm going to do. This is the part of proof 1 and 2 were previously done. So here's part 3. We want to show, here let's remember what we said. Assume the limit as x goes to c of f of x equals to L, and the limit as x goes to c of g of x equals m. And although I'm not going to write this down for this part of the proof, we're assuming that f and g are real value functions whose domain is A, and that c is a cluster point of A. So I'm assuming those things as well. We have this. What do we want to do? We want to show that the limit as x goes to c of f times g acting on x equals to L times m. What I said was we were going to do this using the sequential criteria for function limits. So how can I use the sequential criteria for function limits to show this? Well, this is going to happen if and only if every sequence that's in A, whose none of its terms are C, but converges to C, has the property that f times g acting on that sequence converges to L times m. So we're going to say, let x of n be a sequence in A with x of n being different than C, and the limit as n goes to infinity of x of n equal to C. We must, we're going to show that f times g acting on that sequence converges to L times m. So how are we going to do that? Well, note, the limit as n goes to infinity of f times g acting on x of n. By definition, so Audra, this was something that I think you must have seen by what you said to me earlier. This is the same thing as the limit as n goes to infinity. F times g acting on anything is the same thing as f acting on the input value times g acting on the input value. That's by definition of a multiplication between functions. Okay? Now, here's what I can tell you. Since the limit as x goes to c of f of x equals to L, and the limit as x goes to c of g of x equals to m, then by the sequential criterion for function limits, the SCFL, what that indicates to us is that if you give me any sequence in A, which I am, whose none of its terms are C, but converges to C, then since the limit as x goes to C of f of x equals to L, that means that the limit as n goes to infinity of f of x of n converges to L. And I can say similarly for g of x of n. And will say. And the limit as n goes to infinity of g of x of n equals to 1. This is both by the sequential criteria for function limits. So, the limit, as we've given before, as n goes to infinity of f times g acting on x of n, which we've already said is the same thing as the limit as n goes to infinity by definition of multiplication function of f of x of n times g of x of n. This is the multiplication of two sequences. It's the multiplication of two sequences. What do we know about each one of the sequences? We know each one of them. That's right, is that you, man? Yeah, they converge. And so if you take the limit of a product of sequences that are convergent, that's the same thing as the product of the limits. Is that okay? So this is something we prove as an algebraic property of sequences. So this is equal to L times M. So what have I shown? I've shown this. If you give me any sequence in A, converges to C, but isn't ever equal to C, and that forces F times G of that sequence to be equal to L times M, that means by the sequential criteria for function limits. So using it again, the limit as x goes to C of F times G, A to x, that's got to be equal to L times M. And that ends the third part. Okay, now we should worry about the fourth part. So for the fourth part, we want to show, well, let's make a hypothesis. Suppose g of x is never 0, and that's true for all x element of A, the domain of both f and g. And suppose m is not 0. Okay, we want to show let's go ahead again. We're assuming the limit as x goes to C of f of x equals to L, and the limit as x goes to C of g of x equals to M. Okay, what is it that we want to show? want to show is that the limit as x goes to c of f divided by g acting on x equals to L over M. And so we're going to do this by the sequential criteria for function limits. And so what we're going to do is we're going to let x sub n be a sequence of A with x sub n being different than c for all n element natural numbers, and the limit as n goes to infinity of x sub n being equal to c. Then, if we take a look at the limit as n goes to infinity of f over g acting on x sub n, by definition of division, this is the same thing as the limit as n goes to infinity of f of x sub n over g of x sub n. Now, since the limit as n goes to infinity, as x goes to c, of f of x equals to L, and the limit as x goes to c of g of x equals to M, then using the sequential criteria for function limits, where we've been given this nice x sub n sequence, we have that the limit as n goes to infinity of f of x sub n will equal to L, and the limit as n goes to infinity of g of x sub n equals to M. So none of these terms are 0, and this is 0. So when I look at the limit as n goes to infinity of f of x sub n over g of x sub n, since this is the division between two convergent sequences where the bottom sequence is never 0, and when it converges to is never 0, then by an algebraic property of convergent sequences, we could say the limit of a division is equal to the division of the limit, so it's L over M. And so what did we just show? We just showed, did it give me any sequence in that? That it converges to C and none of its terms are C? That F divided by G acting on that sequence converges to L over M. And what that says is by the sequential criteria for function limits, we have that the limit as x goes to C of f over g acting on x, that's going to be equal to L over M. And that ends the proof. And so we got these algebraic properties for limits of functions by relating it through the sequential criteria for function limits to algebraic properties of convergent sequences. So that's why knowing about sequences helped us get some more information. Does anybody have any questions of me? Okay. Let's take a little second. Does anybody have any questions of me in general about the course? John, did you want to ask me something?
Yeah, I forgot about that.
I did. Okay, while John's looking, does anybody else want to ask anything?
Up there you said so the limit as n goes to infinity of s plus x sub n over g sub x. Why is it different than g sub x? So g of x sub n.
It is supposed to be an n here.
Okay, in the bottom right hand corner.
Here it should be n. I made a mistake.
I just got confused.
Thank you. You didn't get confused. You were correct. There should have been an n there.
Okay.
John?
My question is, so this was in the proof of the SCFO.
All right.
we have the statement 0 is less than absolute value of x sub n minus c is less than 1 over n.
Right.
And you said that if that's true, that the limit as n goes to infinity of x sub n has to be equal to c.
That's correct.
And you said that was by some fact that we had previously used. And I was wanting to know if it was okay if we would use the squeeze theorem there, since we have 0 less than, so 0 and 1 over n both go to 0 as n goes to infinity. So absolute value of x sub n minus c has to go to 0 also.
Right. So that means that distance has to go to c, and that means that quantity, the absolute value, has to be, that absolute value has to go to 0.
Right.
So that has to go to 0. And how does that show that x sub n has to go to c?
I see, maybe it's.
There's still a little something there to take care of, but yes, that is something.
Sufficient.
Yes,
Okay.
it is.
All right, thank you.
So what you're saying here is the sequence that is the absolute value of x sub n minus c goes to 0, and that's
Right.
enough to show, that is enough to show that x sub n will converge to c.
Okay.
But it needs a little bit more work.
Okay, I was just making sure that was consistent with what you had said, because in the video, or when we did this in class, when I had looked back at this, I think you had said it was some different theorem
It is.
that we
I
had.
I am using a different theorem.
Okay.
I'm using a theorem, it's theorem 3.110. It's on page 62, and it's something we've used once before, and we proved it.
Okay.
But essentially, it has to do with if you have a sequence that's the 1 over n, a sequence of numbers that are positive that converge to 0, and that if x sub n minus c inside absolute values is less than that 1 over n, or that a n, really it's c times a sub n, but the c here in our problem is 1.
Okay.
Then that's going to force the x sub n's to converge to x. So it's theorem 1.
I see it. It's on page 60.
Yeah. And that's what I'm using there.
Okay.
And so the proof of that can be mimicked to do exactly what you said about the sequence of the absolute value of x sub n minus c being going towards 0. You can mimic, I think, the proof of that theorem then from there to get that x sub n has to converge to 0.
Or C, I'm sorry. Yeah.
Yeah, to 0. To c, that's right. Is there anybody else with a question or comment? Okay. Well, if you think of something, no worries. Just feel free to ask. But I want to back up just for a second and look at a definition that's listed earlier in the text before these algebraic properties of limits of functions. And that is the problem. Let me move it. Okay. So as a definition, if we let A be a subset of R, F go from A to R, that's a function, the domain is A, and let C be a cluster point of A. We say that F is bounded on some neighborhood of C if there exists a delta neighborhood of C such that, I should say, and a constant, sorry, I forgot to say this, and a constant m that's greater than 0, such that the absolute value of f of x is going to be less than or equal to m, And that's true for all x element of A intersect B sub delta of C. Okay, let's look at some examples of that. Oh. Let's look at 3 examples. Move it out of the way in just a second. Okay. So as examples of this, if we look at f of x being equal to 1 over x, and we note a is really equal to r minus 0. That's the domain for this function. Chuck, I look at 1 over x. This domain's all real numbers except for one number. What can I stick in for x?
0.
0, because if I did, I'd be divided by 0. So that's A. Note, 0 is a cluster point of A. But here's what I notice. Note, f of x is not bounded. I said not bounded on a neighborhood of 0. You can see this pictorially. So that's what f of x, 1 over x looks like. And if I put any neighborhood, no matter what neighborhood I put about C, that's kind of a typical neighborhood about C, where C is 0. This is a neighborhood, a little region about 0. Same distance to the right that there is to the left. If you look at the output values to the right of 0 in this neighborhood, they're shooting up. Here, they're going down. There isn't one fixed number that's positive, such that the absolute value, the output values, all the output values of this region are less than that number. If you said it was 7, no, it's not 7. Because when I'm within 1/8, when I look at x equal to 1/8, you're very close to 0. 1 over 1/8 is 8, that's bigger than 7. Is that okay with this? Okay. Essentially, for any m, x equal to 1 over m, alpha of 1 over m, let's make this equal to 1, is bigger than m. So no matter what m you give me, I get closer to 0 with 1 over m. And, all points even within that region will do it. So no matter what delta you give me, I get something closer to 0 that's within that delta, such that f of that is bigger than the number you gave me. So if 1 over m isn't within the delta units, you just, whatever delta is, if 1 over m is not there, anything within that delta units, 1 over m is not in it, will work. Well, that's one example. Let's look at another example. You know, that limit as x goes to 0, the function I just listed, it doesn't exist. So the one I just did, is limit as x goes to 0. It doesn't exist. Wasn't bounded, the limit didn't exist. Another example, if I let f of x be equal to, let's say 1 if x is greater than or equal to 0, and minus 1 if x is less than 0, then f of x is bounded on a neighborhood about 0. Let's look at the picture. So take a neighborhood about 0. Matter of fact, any neighborhood about 0 will work. So I take this particular neighborhood, and then I'm going to let m be equal to 2. So let's let delta right here be equal to a half. So what's this going? This is going to 1/2. This is going to minus 1/2. Then so for all x element of a, what's a in our problem? That's the domain of this function. What's a? What's the domain of this function? Look at the piecewise definition. For which x values is it defined? All of them. The domain is R. So for all x element of R, intersect v sub 1/2 of 0. Well, that's just really x element of v of 1/2 of 0. So you're looking for minus 1/2 to 1/2. Just look at that region. Okay? Then, the absolute value of f of x. Well, the absolute value of f of x within that region, what are all the output values? They're either 1 or, and you take the absolute value of 1 minus 1. You take the absolute value of them, you always get 1. And that is going to be less than or equal to m, which is 2, in my example. So that's how it's bounded. I can give you the m in some delta neighborhood about 0, so for which the absolute value of the output values will be less than the m for all input values in the domain that's in that delta neighborhood. So that's an example. Let's look at one more example. Oh, I know I've moved the camera, but in that example we just had, let me ask you, what about the limit as x goes to 0 of f of x? Does it exist? No, it doesn't exist. So the two examples I showed you, the limits didn't exist. One of them it was bounded, one of them it wasn't on some neighborhood. Okay? About the same. Let's look at this last example. Let's say f of x is equal to x. We consider, let's make it x plus 1. We consider c equal to 0. Then f of x is bounded on a neighborhood of 0. And you can see this pictorially. If I just look at one unit, that's f of x equal to x plus 1. If I just look at one unit about 0, from minus 1 to 1, look at all the output values. What do they range from? They range from, the output values, the y values, range from 0 to 2. Is that okay? Are all the output values inside absolute values less than some number? Can I find some number that's bigger than those? What's a good number, John? 5. All right. Then, for all x element of R, the domain of this function is R, intersect v sub 1 of 0, then the absolute value of f of x is going to be less than or equal to 5. And that's my m. So there exists an m and a delta neighborhood, such that over that delta neighborhood, the output values inside absolute values is less than that m. Is that okay? So that's when it's bounded. And what about the limit as x goes to 0 of this function? What's it equal to?
Equals 1.
It equals to 1. So the limit here does exist. Is that okay with everybody? So what we've noticed is you could be unbounded. I'm sorry, you could be not bounded. I shouldn't say unbounded. You could be not bounded. And the limit not exist. If, though, when you're bounded, you could be bounded and the limit. Sorry, you could be bounded. The last two examples, and the limit exists or the limit not exist. Okay, so boundedness doesn't say that the limit exists for the function. Just like if you're bounded with a sequence, it doesn't mean that the sequence converges. We solved that for -1 to the n. But we learned for a convergent sequence, if they're convergent sequence, they are bounded. And so here what we're going to learn is, it's a fact. If A is a subset of R, F goes from A to R, and C is a cluster point of A. Then, I should say, we're going to suppose, we're going to let the limit as x goes to c of f of x exist. So it equals something like L. Then, I'm going to write right here. Then, f of x, or f, is bounded on some neighborhood of C. It's bounded on some neighborhood of C. So just because it's bounded doesn't mean that the limit exists. But if the limit exists, it was bounded. That's analogous to what we had for convergent sequences. And the proof of it is going to be somewhat analogous. Let's do that proof. So we're going to let A be a subset of R, F go from A to R, and C be a cluster point. Okay. Also, we're going to suppose the limit as x goes to c of f of x exists. And since it exists, it's got to equal some number. I'm going to say it's L. We want to show f of x is bounded on some neighborhood. C. Oh, okay. Well, since the limit as x goes to c of f of x equals to L, then I'm going to use its definition. That definition was no matter what positive number you give me, no matter what epsilon greater than 0 you give me, there exists this delta, such that if you look at all x's, such that 0 is less than absolute value of x minus c is less than delta, then absolute value of f of x minus L is less than epsilon. But I'm going to pick a particular epsilon, because that's supposed to work for any epsilon. And what we did for the boundedness for a convergent sequence was we let epsilon be equal to, it doesn't matter what we let it, but I can tell you what we did let it be, 1. I'm going to do the same thing. We can let it be something else, it's okay. And here I'm going to say, then, with epsilon equal to 1, there exists a delta greater than 0, such that for all x element of A with 0 less than x minus c is less than delta, then, by conclusion, by the definition of a limit of a function, got just a few more minutes. Then that's the value of f of x minus L will be less than 1. Okay, we want to be want to show that there exists this m and this delta neighborhood, such that for all x element of A intersect this delta neighborhood, that's the absolute value of f of x is less than or equal to cm. Okay, so I'm trying to find this m. And I want to have something about the absolute value of f of x. Okay? And remember, we're trying to find this delta neighborhood. Well, I've got a delta. Okay? But the delta that works for all x's in A. Remember, we're talking about A intersect B sub delta. This looks like B sub delta a lot, except we got this 0 and is less than that. So there's this cases that needs to be brought up. And the cases has to do with C, whether C is in A or not. C is in the delta neighborhood. Is that okay? The distance from C to C is less than whatever positive number you give me, because it's 0. So C is in the delta neighborhood about C. The question is whether C is in A. Is it in that intersection? Well, before I get to that, here, let's note, so for all x element of A with 0 less than x minus c less than delta, here's what we have. I'm going to write down a series of things. This says that f of x minus L is less than 1, but bigger than minus 1, which implies, that minus 1 plus L is less than f of x, which is less than 1 plus L, implying that minus 1 minus the absolute value of L is less than f of x, which is less than 1 plus the absolute value of L. So, for all x element of A, remember that's what we're talking about, with 0 less than x minus c less than this delta, then this statement right here can be rewritten as absolute value. Is the absolute value of f of x will be less than 1 plus the absolute value of L. But that may not be for all x's in A intersect B sub delta C, because there's one more x to be worried about than what's included in here. See, this is all the x's in A intersect B sub delta of C, except possibly C. So we have to break this down into cases. So if C is an element of A, so C is a cluster point. It's either in A or not. Then let M be equal to the absolute value, the maximum between the absolute value of f of C and what I just found, 1 plus L, absolute value of L. Thus, for all x element of the domain intersect this B sub delta of C, B sub delta of C, the absolute value of f of x will be less than or equal to M. But if C is not in the domain of A, I can't use f of C to define M, because it's not defined. F of C is not defined. This is the last thing we'll write. The other case is if C is not in A. Then we define M to be equal to just the 1 plus the absolute value of L. And we see that for all x element of A intersect B sub delta of C, the absolute value of f of x will be less than or equal to 1 plus absolute value of L. So in all possible cases, F is bounded on some neighborhood of C. And that concludes the proof. And that concludes what I wanted to do today. I've held you over just a little bit. It's time to go. We didn't take long enough because the door went open when we got started, but listen, I haven't got everybody's homework. If you have homework to turn in, would like to turn in, please turn it in. It's going to take me a few days to grade it. You should be turning in your homework. Okay? If you want to ask me something right after class about the homework, that sounds okay too. Please turn the homework in too. Thank you very much for your time and patience.